Let's now cover more terminology about binary trees. Specifically, what does it really mean when a binary tree is complete? And we are considering any binary tree with height h, and h over here can be arbitrary, can be 0, can be 1, can be 2, just any height that's not negative. And it will be considered as complete if the following 3 criteria are satisfied. Let's go over the definition. You can make a note of them, and we're going to exemplify and visualize the complete binary trees. Number 1, the nodes with depth h-2 has 2 children, exactly 2. And the nodes with depth h-1, which is 1 level down, may have 0, 1, or 2 child nodes. And number 3 is to say at the same level h-1, they are filled in from left to right. Can you somehow visualize exactly what's going on over here based on these 3 criteria over here? Let's help you with that by illustration right away. And I would like you to focus on just this part of the page. And this part over here is actually for later, about another related shape of the tree, which is called the full binary tree. We'll talk about it a little bit later. Let's focus on the complete binary trees. And let's now look at this particular example tree over here. Why is it complete? Let's now try to annotate the tree a little bit, just to help you understand how to link from the properties of the tree to the criteria we just went over, 3 of them. For this tree, the height is actually 3. Why is that? Because if you look at the maximum depth of the node in the tree, it would be, for example, h will be the one with the maximum depth. It will be 1, 2, and also 3 edges to the root. So the maximum depth is simply 3. And let's go a little bit further. What about in terms of the level and also the depth? You can think about this will be the depth. The depth will be 3, and also the depth will be 2. This will be 1, and for the root it will be 0. So level 0, 1, 2, 3. And let's go a little bit further. Let's try to link the number to the actual heights. And apparently this part over here is the level h. This is level h-1. This is level h-2. Agree? And if you recall, criteria number 1, all the nodes with depth up to and including h-2 has 2 children. So what does it really mean in our example tree over here? That means all the nodes from level 0 all the way down to level h-2. In our case, it would be this particular part of the tree, right? In that case, it would be, let's see, over here. So this part over here are all the nodes in our example tree with the depth less than or equal to h-2. The depth less than or equal to h-2. All the nodes have exactly 2 children. You can see A here has 2 children, and the B over here has 2 children, and the C over here also has 2 children, right? So we are satisfying criteria number 1. What about criteria number 2? Criteria number 2, all the nodes with depth h-1 may have 0, 1, or 2 child nodes. And number 3, we can talk about it together. The children should really be filled in from left to right. Let's talk about it. At level h-1 over here, which would be, let me also annotate it, it would be this level over here, right? You can think about it's here. And this part over here actually got, you can see this node here got exactly 2. And this one actually got 1, and these 2 nodes got 0. It will be valid if the child nodes at the bottom level at level h is filled in from left to right. Indeed, they are. So that's why the tree will be considered as a complete binary tree. Basically, as long as the bottom level over here, you see that it's actually filled in from left to right. Other than that, all the previous level are really the maximum number of nodes. As long as that's the case, then it's a complete binary tree. That's how I thought about it informally. But you should also know about how the formal criteria should be understood. Let's now try to generalize this of complete binary tree criteria. Okay, and I'm going to use this tree over here just in general. And the tree has the heights h over here. And then what we want to do is, you can think about what I have drawn so far up to here is h-1. And I also want to consider h-2 over here, right? So now I got all the relevant levels to be considered. And we say that for all the nodes from level 0 down to h minus 2, down to over here, all the nodes have exactly 2 children. So that means we got a maximum number of nodes, meaning that at level h minus 1, which I'm going to put over here, level h minus 1, we got the maximum number of nodes possible. How many do we have? It should be 2 to the power of h minus 1, based on our earlier discussion. Right? I'm simply using the result we understood from earlier. What about at the bottom level over here? At the bottom level, we got different possibility. It could be that we only got one left child for this first node. In that case, it would be indeed the minimum number of nodes that's possible for a complete binary tree with height h. And of course, if all the nodes at level h minus 1 simply don't have any children, in that case, the height would not be h anymore. It should be h minus 1. Right? Agree? That's something very important to realize as well. So that's why we talk about the minimum versus the maximum. Let's talk about the minimum first. The minimum would be basically we got completely filled out maximum number of nodes all the way down to h minus 1, right? Sorry, I really meant to circle this part over here. That should be up to h minus 1. So what we can do is we can calculate it. It would be 1 plus 2 plus 4 all the way to 2 to the power of h minus 1. And I'm summing up all the nodes down to and including level h minus 1. What about level h? In that case, the minimum will be we only got 1 plus 1. What about the maximum? The maximum is going to be similar. So this part over here is still going to be filled in as the maximum. So that's going to be 1 plus 2 plus 4 all the way to 2 to the h minus 1. But what about the maximum? The maximum will be when this part over here is also completely filled in. Completely filled in, right? So that will be the case for the maximum. In that case, it will be 2 to the power of h at the last level. So plus 2 to the power of h, right? If you do the math and do the simplification, that's exactly the minimum and maximum you will see on the slides over here. All right, so I'm going to let you actually do the, well, actually I can do that quickly together with you. Right, for this one over here, what will be the series over here? It's going to be a geometric sequence. It's going to be exactly 2 to the power of, how many terms do we have? 2 to the power 0 all the way to h minus 1. We got h term. So that'll be 2 to the power of h, and then minus 1 and plus 1. We got exactly 2 to the power of h. Okay. And then what about this one over here? For this part, it's going to be just the same as this one over here. It's going to be 2 to the power of h minus 1. 2 to the power of h minus 1. And then plus 2 to the h. So what would that be? It's going to be actually 2 to the h, 2 to the h, 2 times 2 to the h, which will be 2 to the h plus 1. 2 to the h plus 1, and then minus 1. So these are the minimum and maximum. This is the minimum, and this is the maximum. Right? You can see. I think studying about the definition for the complete binary tree really helps you understand exactly how to count the number of nodes. And of course, we have done that in detail from the earlier part of the lecture. Right? Hopefully you're okay about the complete binary tree. And let's now move on to the other kind of binary tree, which is the full binary tree. Let's now go back to the slide to see the definition. So a binary tree with height h, again, h can be any arbitrary natural number as long as it's not negative. It will be considered full if just one criterion. Each node with the depth h minus 1, basically the second last level, has 2 child nodes, really the maximum criterion that we spoke about. Let's see example right away. And I think if you already understood about the full binary, about the complete binary tree, the full binary tree is basically just a special case where at the bottom level over here, of course, it is still filling from left to right, but you got just the maximum number of nodes at the bottom level as well. That's really the essence for the full binary tree. But let's still try to relate to the definition over here. So here we got the height is actually h is actually equal to 3. In that case, we actually got, so 1 here and 2 here and also 3 here. So that's the height, right? And also we got, let's talk about the depth. So this will be depth is equal to 3, the depth is equal to 2, the depth is equal to 1, the depth is equal to 0. And this part over here is really the h. And this is really the h minus 1. And we're only concerned about h minus 1. And the definition is all the nodes at level h minus 1, which I'm going to highlight right away. All the nodes over here down to and including the level h minus 1, all of them should have 2 children, right? You just remember not just the level, but it should be each node with depth less than or equal to h minus 1, meaning that the levels starting from 0 all the way down to and including 2 must have all its nodes with 2 children. So you can see this node must have 2 children, and this node over here must have 2 children, and this node must have 2 children as well, right? And also these nodes are still less than or equal to h minus 1 depth, so they should have also 2 children. So this will give you the maximum tree that we spoke about just earlier, this case over here, right? This is the maximum tree that we spoke about earlier. So this case is rather straightforward. Let's talk about the general case quickly. And in the general case, let's say this is the tree of heights h, and we talk about h minus 1. So that means down to over here, we got basically all the nodes filled in. Specifically for the level h minus 1, we got this completely filled in, and all of them got exactly 2 children. Okay, I just want to draw in front of you just to make sure you understand that. So this is the first node at level h minus 1. In that case, they got 2 children. All the way to the last node at level h minus 1 also got 2 children. And what would be the minimum and maximum? Well, I can talk about both of them at the same time. The criterion for a full binary tree is very strict. There's really no notion. There's really no freedom as to the range of the number of nodes for the full binary tree. The minimum and maximum happen to be just the same. It has to be exactly the maximum, right? So the minimum and maximum is really the same number over here, right? Just the same. What would that be? Well, it's going to be 2 to the power of 0 for level 0, and to the power of 1 plus all the way to 2 to the power of, this is level h over here, and the maximum number of nodes at level h will be 2 to the h, right? And plus, so that will be 2 to the h, which will be equal to, how many terms do we have? We got 0 all the way to h. So we got h plus 1 term. So that means we got 2 to the power of h plus 1 and then minus 1. I simply just apply the formula for geometrical sequence. If you're wondering about exactly how this number can be applied, you should really review the formula, which we spoke about in detail earlier. So this will be the minimum and maximum at the same time. 2 to the power of h plus 1 minus 1. 2 to the power h plus 1 minus 1. And this number simply match the maximum case of the complete binary tree. Again, a full binary tree is a special case of complete binary tree. However, a complete binary tree is not necessarily a full binary tree. For example, you can see this complete binary tree over here is not completely filled out at the last level. In that case, it's not full.